record this. So actually, that was a very good question, Paul. Thanks. So this is something to do with if people are gonna talk in this recording, then there is some permissions that are needed from you guys. But I just started recording, so we lost an hour, but that's okay. So I just started recording. Maybe they'll send a link to me or to all of you, and I'll share it with you. Okay. So let me get back. Where was I? Okay, so I was just talking about a linear model, Wx plus b. So we're going to change the models later, but for now, let's say the model is Wx plus b. Then what is the output of this model? So this is a model which is taking an input x, d-dimensional vector, and has these parameters. Let's say the parameters we figured out the numbers. Then the output of this model is actually a p-dimensional vector, right? P-dimensional vector of numbers. So these p-dimensional vector of numbers, you can think of them as scores. Okay, I'm going to use the word scores, and I'm going to refer to it again and again. So given these p scores, you can actually you can actually finish your classification task. So how do you do that? So let's say we somehow know the numbers in W and B, and now somebody gives me an x. Let's say x is 0.325. Maybe D is 3 here for simplicity, and let's say P is also 3, or okay, let's say P is 4, just to not make it simple. So P is 4, so I produce 4 scores. Okay, so I produce 4 numbers essentially. This F produces 4 numbers. Let's say the scores are 1, 5, 3, and 2. So there are 4 numbers, and then as a very obvious thing that you can do is to pick one of these numbers as your pick the index of the highest number to be your class. For example, because there's the highest number is in second coordinate, you can say my classifier is outputting class of this input to be, or the class label of this input to be 2. Okay, so that's what this argmax means. If you have any questions, definitely type it on the chat. Okay, so that's one intuitive way you can figure out a classifier. Pick a model and use that for classification. Now, what's left is we've specified a model. If in this example, a linear model, and what is left to do is to figure out the best choices for W and B, and figure out the best choices for W and B. And to do that, we have another question to ask, which is what is meant by best. Okay, and so the definition of best is captured by the loss function. And how do we get the best choices for W and B is the task, is essentially optimization. So let's talk about loss functions. So let me use a notation Sj for the jth coordinate of this classifier function f. And I'm going to define, so what I'm going to do is, so for every x, this classifier produces a bunch of scores, p scores, right? P scores. So I'm going to define this loss function, loss over the training data, which will be a loss for every choice of W and B. W and B are the parameters. If I change the parameters, I need to get a different loss value. Okay, so in particular, I'm going to choose the loss value as L data, which is what I'm defining as the sum over n terms, and there's an L for each term. Okay, so n terms because there are n examples, and for each example, I'm going to define a loss value. Okay, so that's what I meant by decomposable over n terms. So I'm going to define a loss value for each example in my training data. Okay, so let me talk about the first type of loss, which is the first choice that you can make for Li. It makes sense for binary classification tasks as well as multi-class classification tasks. And the choice is Li is equal to the negative log probability of what the true class is, which is Yi, given this particular Xi. So remember, in my training data, I have Xi's and I have Yi's. Okay, so for a given W and B, I produce a bunch of scores. From those scores, I can think of from those scores. Let's say in this example, the score for the second coordinate is the highest. It means that the probability that I'm predicting class 2 is is high in a very crude sense. So, but the real class for that example could be here, for example, let's say the real class is actually coordinate 1. I'm predicting 2 because for my choice of W and D, 2, the second coordinate was the highest with the number 5. And so I'm predicting the second class, but I also have a probability associated with the first class, which is maybe very low value. Okay, but the true class is class 1. So the loss for this example, the loss, which is a scoring that I'm giving for W and D for this example, is that what is the probability that is being assigned to the true class, in my training data. And as we just discussed, maybe for that example, the true class was the first coordinate, and we were predicting a low probability value. If the remember, all probabilities values are anywhere less than 1, and hopefully greater than equal to 0, right? So if the p value, this value is low, which means closer to 0, then the log of number, which is very close to 0, is going to be highly negative. Okay, and negative of that highly negative number is going to be highly positive, in the sense that the loss value is going to be very high if you don't predict the right class. Okay, so that's what you can directly interpret that from this expression for Li. And here I'm just showing the relation between the probability values and the scores themselves. So let me write it. Yeah. So all I'm saying is F. So F is going from X, let's say it's 3 cross 1, to a value which is 4 cross 1. Okay, so let's say, which means that there are four classes, and this is the input X. Okay, X belongs to R3. Okay, three-dimensional input, four classes, and F has parameters W and D. For a given choice of parameters, all I'm saying is there's going to be, so there's four F is going to produce four numbers, which will be score 1, score 2, score 3, and score 4. And these numbers, and we saw that F was essentially equal to Wx plus B, right? And so X is, could be any real number. Each coordinate could be any real number. So F is not necessarily, so the scores need not necessarily be between 0 and 1. That's what I want to point out. Because they need not be necessarily between 0 and 1, and that's true because it's just a linear function. And so to sandwich them back to 0 and 1, you can do a transformation, which is maybe for the first coordinate, I'll do S1 e to the power S1 divided by e to the power S1 plus S2 plus S3 plus S. Okay. So the nice thing about this is that if I do this transformation for all the four coordinates, so this is still 4 cross 1. So once I get the scores, I can take the four scores and compute the first coordinate, second coordinate, third coordinate, fourth coordinate. They sum to 1. And you can see that, right? In the numerator, I just have the first term here. In the second one, I'll have the second term here. The third guy, I'll have the third term, and e to the power S4. So since, I can sum and it sums to 1. So it looks like a probability. Okay. So that's the that's the expression, this expression. That's this expression here. Okay. And similarly, you can interpret what this loss means and why is it high or low, depending on whether you misclassified or not, and makes sense for a binary setting. So that's loss functions. In addition to loss functions themselves, which are a number that you assign for each, typically assigned for each training example, you'll also have a need for what is called regularization. Okay, and regularization makes sense when, for example, there are multiple models which all lead to the same L data, right? So where is that? It could be the case that there are two linear models which both lead to the same L data value. It could happen. And then to give a preference over one model versus the other, then you can add what is called regularization. Okay, and that preference is like if you have a desired model. You can also add regularization to control overfitting. And there's going to be some new regularization techniques that you'll see in this course. For example, let me just teaser. something called dropout is a way to regularize. But let's go back to the typical way, I mean, the type of regularization that you've seen before. So what you do is there's a score that is only dependent on the training data. And then there's a score which depends on your preference. Okay, so that doesn't depend on the training data, but depends on, oh, if you chose a certain value of the weight matrix, certain value of the W parameter and certain value for the B parameter, then there's a particular score. Okay, this is not data driven. And there's a, so lambda is a number which is some positive number that just controls how much you prefer, how much you prefer a non-data based preference, right? Which is the second term, and how much is that W and B choice scoring in terms of with respect to the data. So so that's the final loss. And here are some examples. So for example, a regularization that you've seen in, for example, ridge regression is L2 regularization. So if you regularize, let's say, let me pick the first parameter W in that linear model, then L2 regularization for W happens to be a matrix here instead of a vector. And so I'll just add up the squares of the entries of this matrix. Okay, that's L2 regularization. Similarly, adding up the absolute values of the entries would be L1 regularization, and so on. Okay. So with that, so that's the definition of loss. So with the appropriate choice of regularization, you figured out what is the final loss. Okay, so that's how you would say which model is good. Whether W comma B pair, one particular pair is better than another pair of W comma B. Now, so the last part, which is to find, how do we find the best choice of W and B pairs, right? So that's typically done using optimization techniques. And this is something which, at least in my version of 575, I skip because it is something computational. And you will not see it if you're using pre-existing packages. But we'll see one particular way to optimize for the best W and B choice. The best candidate W and B, best, as I said, minimizes the loss function, or the loss plus the scaled regularization value. So here's a picture. So you have these n examples from which you take x's, right? And for a given W comma B, these x's make some predictions, right? A bunch of scores, and the scores plus this the true y's that you know in your training data lead you to the loss value, right? Not just that, not just this part is the data part, and this part is the regularization part. Or this part is just L data. So, and then you have parameters W comma B, which determine of course, the scores, and therefore L data, and therefore L. But the parameters also determine the regularization value, and therefore the final score as well. So, and in this slide, I'm just showing that you don't have to explicitly think of W comma B. And there was a reason why I used W comma B. In particular, the reason is that this is actually the model we're describing. If you, some of you may have this hunch before, is that it is just a logistic regression model. And we can talk about more about why this particular definition of F gives rise to a multi-class logistic regression model. But we'll do that maybe a bit later. So if instead of W comma B, I represent it as a generic parameter theta. So not every model is a logistic regression model with a linear functional form, right? So then you just call it, I'm just changing the notation to a general form here in this slide. Now, let's look at how do we optimize. How do we choose for the best? So optimization is all about finding the best W comma best in terms of what we just defined, loss function. So there are many ways to optimize, especially we're going to be concerned with mostly differentiable models. And I'll tell you, so we're going to use some, I guess, some notation or some terminology from calculus. In particular, what I'm trying to say is that there are many ways to optimize, but one particular way that we're going to look at mostly in this course is going to be what are called first order methods, or methods which use the gradient information. Okay, so this is the keyword, gradient. I guess differentiable function is also a keyword. And so we're going to use gradient information to optimize. And what is a gradient? Just to recap, a gradient is just a vector of partial derivatives of a function with respect to something. So in particular, we're going to care about the vector of partial derivatives of the function with respect to its parameters theta. Okay, so so that's what a gradient is. It's a vector. If theta is a vector, if theta is two-dimensional, there's going to be a two-dimensional vector, and so on. And it can actually compute gradients numerically. So since it's a partial derivative, so remember, so let's say theta is a two-dimensional. Yeah, let's say theta is two-dimensional. Then how do you compute a gradient numerically? Is that you keep one of the, so you compute a gradient at a given theta value. Okay, theta is equal to something, theta fixed. Okay, so you compute gradient at a given parameter value. So what you do is at a given value of theta, you're just trying to find out, oh, if I perturb the first coordinate, how much is my output going to change, essentially. So that's the numerator here. So it's essentially the rate of change of the output. The output is basically every time I change theta, f changes, or f's evaluation, given it's x is fixed. X is fixed changes. So it just quantifies how much does the output change as a function of the choice of theta. Okay, keeping everything else fixed. So there are numerical ways to find this gradient, but the more clever thing to do, and that's what you'll see many of the software packages do, is to analytically compute the gradient. And to do that, a good tool technique is the chain rule, and that's the underlying idea behind backpropagation, or backprop for short. Okay, and we're going to discuss that pretty soon. So let me finish this optimization part. So what's the intuition for how? So if we had gradient information, how do we optimize for w comma b? So the idea is you start from w naught comma b naught. Okay, you start with some arbitrary values for w naught comma b naught, which means that this is a candidate model. Okay, we can get a score, right? But at this candidate model, we can also evaluate the gradient of the output, the gradient of the loss function with respect to these parameters, right? So which is we evaluate L. We can get a score for this model itself, but we can also get the gradient of the loss or the output with respect to the current parameters. Then what we do is using the gradient, we can, and I'll show you how to use the gradient, but using the gradient, we can go to a new parameter choice, which is W1, B1, such that with the hope that the new parameter's corresponding loss value is smaller. Okay. And you keep repeating this in a for loop, and that's how you would do a what is essentially a gradient descent optimization strategy. So all I need to specify now is how do you go from W to W naught B naught to W1 B1, and as I said, the gradient of L with respect to the parameters is what is lets us go from W naught to W1. So let's look at an example here. So I'm going to look at a particular version called batched gradient descent. There are actually many variations. Here I'm just going to give the intuition for one of the techniques. So so first you start. So what you do is in each so there are a few words here. So one is gradient descent, which is gradient descent just means going from something like W naught B naught to W1 B1. Okay, so that's what we want. Batched is just an adjective which says that I'm not going to use the all my training data, so x1 all the way to xn, y1 all the way to yn. I'm going to use only a part of it. Okay, it's a batch, and just think of if my n is 1,000, but if we only use let's say 256 observations, then that's a batch. Okay. So AlexNet is, I think I briefly mentioned AlexNet was the neural network which did well in the 2012 ImageNet challenge, for example. So let's say we use 256 examples as one batch. So then what we do is we are not computing the gradient of L itself, but just L1 to, remember L is equal to L1 plus L2 plus L256. Okay, so L is not just 256 plus all the way to L, let's say 1,000, if there are 1,000 examples. Instead of that, I'm going to only find the gradient of L with respect to the parameters. I'm putting theta here with respect to only a part of the definition of the L. Okay, so this loss function. So in particular, the gradient of L with respect to the first parameter W and the second parameter B. Okay, and so the so I can find the gradient with respect to W and gradient with respect to B. And then I'm going to update from the previous values of W comma B pair to the new values of W comma B pair in an additive fashion like this. So once I find the gradient, it turns out the gradient, and this is the fact that you check, the gradient dimensions are the same as the parameter dimension. Okay. And I said that somewhere here, where I said if theta is two-dimensional, then the gradient will be a two-dimensional vector, right? So the dimensions match. If this is a 4x3 matrix, this is also going to be a 4x3 matrix. And so this is how you would go from W0 W0 B0 to W1 B1. Okay, and here is an example in one dimension. So actually here theta is one dimensions R1, and here you can see that gradient turns out to be just the tangent. Gradient is so gradient. So let's say at a given point, this point, let's say this is a particular parameter W0, or yeah, let's say W0. Then gradient is going to be just a number essentially, which will go to the go in the right, go to the left with some magnitude. Okay, and so you will maybe get to W1 here. So the gradient space is in the space of the parameters. Okay, it's in one dimension here. So that's gradient-based optimization. This is just an intuition. We're gonna get into the details in the course soon. There's one thing, the last thing to recap from your 575, 572 is the notion of cross-validation. Okay, so cross-validation is basically used to figure out some choices that you cannot differentiate, for example. So typically the choices, for example, the regularization parameter lambda, should it be 10 or 1 or 0.1 or something like that. So there'll be some discrete choices. These choices would be for lambda would be the choices for the hyperparameter lambda. And you can find a good choice for lambda, make a good choice for lambda by breaking data sets into multiple folds and leaving a fold out, training on the rest of the fold at a given choice. So let's say lambda is 1, at a given choice, training the rest of the fold and making a prediction on the left out fold and getting a score and averaging those scores. I'm not going to describe cross-validation in detail here, but I just wanted to put that as part of optimization, because in the previous slides we saw optimization of the differentiable parameter. So let's say W and B. In this slide, we're just saying that you can also optimize for discrete parameters like lambda. I'm just calling them, we're calling them hyperparameters here. Okay, I think that somehow my writing vanished, but okay. So any questions at this point on the chat, or if somebody wants to use the mic?
I have a quick question regarding the batch training. So
yeah.
if the we have like 1,000 data points and then we are gonna train the model using batch,
Yeah.
does that mean we are using only 256, for example, to train the model, or are we gonna parse in data in batches, like in?
Yes, great question. So the question, just to repeat for the other folks, is basically how do we use a batch in a batch gradient descent routine? So if we have 1,000 examples and let's say our batch size is 256, or let's say 100 for simplicity, then I'm just using the first 100 examples to determine the gradient of L with respect to my current parameter choice and gradient of the loss function with respect to the parameter. These two numbers is what I compute using just 100 training examples instead of 1,000. I compute this. Maybe I go from W0 B0 to W1 B1. Okay, now I have to repeat this procedure again. So here I need again gradient information. So just like here I use this gradient information, here again I need this gradient. So here I could do several things. For example, I could choose the next 100 examples as a batch and find this gradient, or I could randomly sample 100 observations and find this gradient. So we will, so you can do various different things. Actually, you'll see that most likely what people do is use the first 100, use another 100, use another 100, all the way to the 1,000, and that's called a pass. You do one pass over your data, and you can do multiple passes. After you hit the 1,000, you can again go back and start use the first batch, for example. Okay.
So if we are using this batch mode, are we selecting these data points 256 randomly, or are they in a order that first 256?
Yeah, so in typical in typical code bases or scripts that we will see later, we are actually doing it without randomness. Okay, but you can actually do it with randomness, and that's essentially stochastic gradient descent. Okay, with the batch size. So there's some, so GD just represents gradient descent, and there's a particular variant of this algorithm called stochastic gradient descent, where, remember, we don't really care about batch. Ideally, we should be using the gradient of L with respect to W should be computed. Remember, L is a function of all the n examples. There was a summation over I is equal to 1 to n of Li, right? So it was a function of all the n examples. Instead of that, we are just saying that, oh, this computation of finding gradient with respect to everybody may be difficult. And so I'm just chopping it off. Instead of up to n, I'm just saying do it up to 256. Okay. So we can do randomly, we can do part by part in a sequential manner without any randomness. It's all fine. I mean, these are all empirical observations, by the way. So if you're looking at the theory of these types of first order schemes, how do they work with different ways of batching? That's a different question.
Thank you.
Yeah. Any other questions?
Following up this one more question, Professor. So are you going to take the average of all these losses up to the 1,000 sample, or are you going to dynamically update the losses and find the next 100 and so on?
So let me use this to kind of, so maybe I didn't, so today's lecture was just to motivate, I mean, so you guys must have not seen optimization, at least in my version of the 575 or previous courses. I don't generally talk about the computation that goes behind finding the best parameters for any model. For example, in this discussion, we've been using logistic regression, right? Wx plus b, as I said, I'm claiming that this is a logistic regression model. We'll check it again later. So for this model, if your question is, remember, whatever be the model, whether it's logistic regression or not, remember L was equal to sum over I is equal to 1 to n. N is the number of training examples. Let's say n is 1,000. Li plus a regularization term, which doesn't depend on, maybe depends on just the parameters, but, could be only depending on W, or could be depending on only on B or something. So this is not dependent on data. Okay, so there's nothing to do with data. The batching happens, ideally, I want to do this. Okay, so I want to find W1 and B1. This is going to be my update scheme. Ideally, I want to do this, which is something says okay. Is W0, B0, some random choice that I chose, a random choice of parameters, candidate parameters that I chose, minus some alpha. Let's say it's, instead of alpha, let me just say, let's say minus 1 by 10, some number. Okay, times this gradient of L. L is exactly defined this way, right? Gradient of L with respect to W times gradient of B with respect to gradient of L with respect to B. Okay, so this is what I want to do. But to do this, I need to find the gradient of this whole expression. I mean, see this, there's an L here. Li also depends on L. Li also depends on W, and there's also W here. So the whole thing, you can find its gradient with respect to W. Okay, but what I'm saying is in batch gradient descent, batched GD variants. Okay, it's not one unique technique anyway. Gradient descent, the first order family has many techniques, many ways of using the gradient. In the batched version, what you do is you just say, I'm going to approximate, I'm just going to approximate L tilde as as a way to which approximates L. Okay, and so this L tilde is just going to be some 256 guys. Okay, I is equal to 1 to 256 of some Li. So okay, let me just use J because these i's are not exactly the first 256 guys, but it could be any 256 numbers. Okay, plus the same. This will be the same because it doesn't depend on data. And I'm going to find the same update rule, but the minus 1 by 10 times the gradient of W of L tilde. That's all. Okay. Now, which 256 I'm going to use to define this gradient is my choice. It could be a random 256 examples, or it could be the first 256, the first iteration, because there's one iteration. Okay. So from here, I need to go to W2, B2. So in the next iteration, maybe I'll choose the next 256 and so on. Is that clear?
Yeah, it's clear. Okay.
I thought batch is when you update the parameter after a full training set. Isn't I think
so don't worry about the terminologies. Don't get confused about terminologies. Here I'm just talking about the batch as a batch size while doing an optimization, while applying this optimization technique. Okay.
Okay.
There are different people use different have different intentions when they say batch. Here, a batch means a subset of your full training data. Okay.
Okay. Cool.
Any other questions on chat or anything? Okay, actually, let's take a break. I thought we'll take a break at 4:30, but it happened to be 5. So let's take a break for 10 minutes and resume at 5:12. Okay. Yeah, in the meantime, if anybody has questions, feel free to ask. Okay. Okay, so I assume everybody's back. Okay, so what I'm going to do next is first show a simple demo that you can try out after this lecture. So I don't know how many of you saw this demo before. It's at this link, which is on the schedule lecture 1 material. So we're going to look at these notebooks pretty soon, which talk about the linear classifier that I've been mentioning earlier. So Teachable Machine is a nice demo of doing two-class classification or even more, um, where you can actually in real time uh, do these things, which is essentially gather some training examples, which typically is your images, uh, like you standing versus sitting or whatever, and then you can train a model in the browser, and then you can do some real-time classification using your webcam. So I'm not going to show this demo because I think it's fun to you guys to explore it yourself. Um, what I'll do is get back. Okay, somebody asked a question. So let me first share my. So the question was, how time consuming will things be? So how do I see the chat? Yeah. So how challenging or time consuming will the assignments be? Because it's a group of 4 students, the number of questions is about, the first assignment seems like a little bit more questions, but each question is, it's easy to do. It's mostly checking your familiarity with Python and the notebooks that I have shared with lecture 1. Each assignment should take about 6 to 10 hours. Okay. So you have a 2-week period within which you can solve the assignment, and you have Slack as well as you can contact, from which you can contact others as well as teaching staff. I think it's definitely doable. It's not on the heavy side. So there are only 4 assignments. So I would say it's not going to be time consuming given 4 students. So, but I think earlier I was mentioning that somebody was asking, is the knowledge of 575 very critical? It's not. What is critical is I know many of you might not have worked with Python before, so I think getting up to speed with Python would be good. Most of the questions and assignments are coding in the sense of training a neural network of different types. Okay, that's what most of the assignments are. Um, but maybe there's a question here and there for which you need a textual answer, but you can just write the textual answer in the Jupyter notebook, for example, if you're using one. Okay. So there is actually a template for the assignment for assignment 1, which is essentially a Jupyter notebook. So I'm going to talk about Jupyter notebook pretty soon. Let me tackle a new topic called backpropagation first, and then I'm going to talk about Jupyter Notebook and show linear regression. Somebody's asking, so David is asking, will there be emphasis on proofs? Actually, there are no proofs. So most of deep learning, at least we are going to look at, is essentially come from an applied ML perspective. And so there's actually no proofs, no expressions pretty much, except for this first lecture to say what is the loss function and so on. But most of it is actually intuition driven and doesn't need any notation or uh, proofs or claiming anything. Okay, so there is not going to be much derivations. Maybe there will be some expressions that's needed when we look at a specific model called variation autoencoder, but that's several lectures from now, and we'll visit it when we get there. Okay, but at the same time, you should not, this course is not is after 575, so you should have a decent familiarity with the basic models to see let's say in every lecture you see a new model. It should not be completely alien. That's all. So with that, let me get back to the lecture. Uh, so no proofs, but at the same time, yeah, there basically no mathematics involved. Not much. Okay, there's a little bit of calculus and linear algebra, but that's not. That's just for conceptual understanding. Everything to aid conceptual understanding. Okay, so let me talk about backpropagation. It's not a very difficult topic. So backpropagation is essentially a way to break down your computation of your gradient. So remember in the previous, I guess, slides, I was talking about, oh, let's get the gradient of L, which is the loss with respect to W parameter, or let's get the gradient of L with respect to the B parameter. Once we have these two, we can make changes to our linear model candidates and hopefully get to the best model eventually, after some iterations. So backpropagation is about how to get this guy or this guy, efficiently. I wouldn't say efficiently, but yeah, good. Efficiency is also there. Efficiently, or by breaking down the problem. Basically breaking down the problem of computing a gradient of the loss with respect to parameters into smaller steps, and then somehow stitching together a solution, which is a gradient from that. Okay, so and this is just to say that backpropagation is essentially, for those of you who are a little bit who remember calculus, so it's essentially the chain rule. So we'll look at an example in the next slide, but the mental picture you should have is, let's say there's a computation. Okay, so I'm not going to talk about the loss and the parameter here at this moment. Let's say there's some computation happening, which is H. Okay, H takes two inputs, A and B, and produces an output. Okay, so some value. So H itself is a value. So A and B go in, and out comes a value H. Okay. Now, what is the so let's say that H is subsequently used in the computation of a value called G. Okay. So we started with A and B. Those were our inputs from which we got an intermediate value H, and from there we got a final value. Let's call it G. Okay. Now let's say, so this picture here is representing the computation H. Okay, so it's representing using a graph notation. So this big circle is like a node, and there are two inputs, this one A and B, and there's a blue output H. Okay, so it's a node with two incoming edges and one outgoing edge. Okay, so it's going to be a node in what is called a computation graph. And the simple idea here is that if this node, so eventually, so what we care about is getting gradients, right? So this is a node, in a computation graph, and if it somehow has access to the gradient from its successor. So if the computation is happening where I input values A and B, some intermediate number H realizes, from which a final number G realizes, then if I know the gradient of G with respect to H, okay, that's the, H is being passed on to get G. If I know the gradient of G with respect to H, and if I know my local gradients, okay, local gradients are gradient of H with respect to its input A, and gradient of H with respect to its second input B. If I know these two local gradients, then I can compute the gradient of G with respect to A, and the gradient of G with respect to A is just computed in this way. Okay, so what is the objective here? I think I missed the objective part. So we want to find the gradient of G with respect to A and gradient of G with respect to B. Okay, and local gradients, because the computation node H knows its function. Maybe it's A plus B. Then you know what the gradient of, if the H is equal to A plus B, then you know what the gradient of H with respect to A is. It's 1, and the gradient of H with respect to B, it's also 1. So you know local gradients somehow, and we're going to look at an example soon. If you know the local gradients, you can take the incoming gradient from your successor node and just multiply them together, and you'll get the gradient of the G with respect to A. And this multiplication is essentially chain rule. Okay, so let me explain that again in a, I should have drawn this. Okay, again in a, with the example. So let's say H, so let's drop H. Actually, yeah, H, this is H. So let's say G has now, it has three, is a computation which has starting points as three inputs, A, B, and C. There's an intermediate computation H, which is A times B. And I think yeah, H is A times B. And then G is equal to H plus C. Okay, G is equal to A times B plus C. Okay, so this is a very tiny computation graph. It's just saying that there are 3 inputs. Ultimately, something is computed, which is G. Okay, now the question we want to ask is what is the gradient of G with respect to A, gradient of G with respect to B, and with respect to C. Actually, by just looking at the function, you guys can eyeball what the gradient of G with respect to C is. For example, with respect to C, it's 1. Okay, with respect to A, it's going to be B. With respect to B, it's going to be A. Okay, whatever the current values are, right? So you can just eyeball, but what we're going to do is do a backprop step. So that's captured in this slide. So what we're going to start with is the final output G. So gradient of G with respect to itself is 1. Okay, so this is our starting point. Okay, and we know that G is equal to H plus C. So whenever a function, we know that when a function G is equal to H plus C, so G's input is H and G's input is C, right? Those two things, H and this C. Okay, so now what is the gradient of G with respect to H? Okay, by just eyeballing here, you can say the gradient of G with respect to H is 1. Okay, because if I change H by 1 unit, G also changes by 1 unit, keeping everything else constant. Okay, that's what gradient is. So that's what I wrote here. Gradient of G with respect to H is 1. Gradient of G with respect to C is 1 because G has this functional form, this simple relation between the output and input. Okay. Now, therefore, what I can do is find the gradient of. Okay, let me move forward actually. So this I computed. Now, what is the local gradient of? So this is H. Its input is A and B. What is the local gradient of H with respect to A? So that's B. And local gradient of H with respect to B is A, right? So this is also clear because H is just A times B. So let's say I fix B to be a fixed number. If I change A by 1 unit, H changes by B units, right? So that's why the gradient of H with respect to A is B, okay? So these are the local gradients I computed. So now we want to find what is the gradient of A, G with respect to A, B, and C by chain rule. Chain rule just means the gradient of G with respect to gradient of, let's say, A is gradient of G with respect to gradient of H, sorry, gradient of G with respect to H times gradient of H with respect to A. Okay, so by the way, this notation is partial derivative notation. You can also use other notations if you want. Okay, so it's like an inverted 6. Anyway, gradient of G with respect to A is but chain rule just means you take the local gradient times another local gradient. Okay, and so we know, so therefore the gradient of G with respect to A is B times 1. Actually, you can also do this if you want, but B times 1, which is B. Okay, so this is equal to B is equal to A is equal to 1. Where B, so when we say gradient, we are talking about a gradient with respect to the current values. Okay, at A, B, C is equal to whatever, it's a 10, 5, and 7. So you actually substitute these numbers and you will get the gradient at the current value. Okay, but for general input, we have computed the gradient. So if you have any questions, put it on chat or you can ask. So we're going to go to the next example. This example seems a little bit more involved, but it's actually the same idea, which is, let's say G has now 4 inputs, A, B, X, and Y. And G takes A and X. So first you take A and X, multiply it to get intermediate value C. You take B and Y, multiply it to get an intermediate value D. And then you add them to get a value Z. So this is Z. And then you do looks like a crazy transformation, but it's 1 by 1 plus e to the power minus Z. Okay, that's the transformation to get G. Now, what we care about is trying to find the gradient of G with respect to A, right? So by just looking at this expression, without looking at this this particular graph in the red box, you can directly apply a chain rule from calculus to find the gradient of G with respect to any of its inputs. Okay, but what we can do is find local gradients. For example, we can find the gradient of G with respect to Z, its input. Okay, for this, I mean, I just put a ton of computation inside this big, inside this blue node here. You can actually split it into multiple small nodes, but for this, it seems like one input, one dimensional input, one dimensional output. What is the gradient of G with respect to Z? That if you compute, it's actually equal. So I think okay. So here in this example, I'm using specific values of A, B, X, and Y to keep things simple. So if you start with A, B, X, and Y as 2, 1, minus 3, 4, you can get the intermediate numbers and get the final number. What is G? But so at these values of A, B, X, and Y, the local gradient of G with respect to local gradient of Z is equal to this. Okay, so we're not going to do that calculus computation here, but that's the local gradient. Okay, so you guys can verify it offline, or we can take it off after the lecture finishes. So that's local gradient, and then what we do is find the local gradient of Z with respect to its inputs C and D. Okay, so local gradient of Z with respect to C is 1, because remember Z is just C plus D. So yeah, so local gradient of Z with respect to C is 1. So what you do is multiply 1 times the incoming gradient, which is the gradient of G with respect to Z. Remember, it's the same expression. So that will give us the gradient of G with respect to C. So we went from this guy all the way to C. And similarly, what we want to do is go from this guy all the way to A. Okay, and what you do is multiply a bunch of local gradients. So that's the local gradient of G with respect to C. And since there's a multiplication happening, the local gradient of C with respect to let's say A is X. Okay, so whatever the X value, minus 3 times this whole expression is the gradient of G with respect to X. Okay, you can sorry, gradient of G with respect to A, because right here, gradient of G with respect to gradient of A is with respect to Z times gradient of Z with respect to gradient of its input. What is it? C times gradient of C with respect to gradient of A. That's a chain rule. But what we want to take away from this part of the lecture is not the analytical computation of these multiplications, but just looking at the graph, you want to get some patterns. Okay, the patterns are, let me skip over the computation in this example because we saw computation of G to A. The other computations are very similar. The patterns are basically that when you have a huge computation graph, maybe there's a node, maybe there's another node, lots of computations going on, right? And maybe at the end of the day, you got a loss value. Okay. Now, to get the gradient of L with respect to some, let's say some input, okay, maybe A and B, you don't have to worry about the whole graph to get it at the same time. What you care about is to look at each node individually and do some local computation. And that is illustrated, for example, in this slide. Okay, actually, you do some local computation. The local computation was actually shown in the first slide itself, which is this: that whatever be the computation node, as long as you know what is happening in that node, you know the local gradient, which is the gradient of its output with respect to its input. That you can always compute. And to compute, to the backpropagation part, it just means that if you want to find, maybe there's a global operation going on where you want to find a gradient of L, which is let's say the loss function with respect to, let's say, parameter A, then you just need to take an incoming gradient from somebody else who used a computation. So H maybe was an input to G, and G maybe itself is a loss. So take an incoming gradient, multiply with the local gradient, and then pass it back. Okay, keep passing it back. So the local node just needs to get a gradient, multiply with its local gradient value, and then pass it back. Okay, that's what you should do. And as long as every node does this, from, let's say, the final computation L all the way back to whichever gradients you care about. Here we care about, let's say, gradient of G with respect to gradient of A. You can compute that just by doing this local computations at each node. Okay, so some of you may say, okay, this seems, why is this correct? This will be correct as long as the graph is some sort of what is called a directed acyclic graph. Okay, as long as things are not circular, like I pass some information here and it goes back here and goes back here, as long as it's not like that, and then which is what is meant by acyclic. Directed just means there is a direction of computation here. You see those edges. So as long as you have a graph like this, you can compute gradients by just multiplying local gradients with the incoming gradients. Okay, so that's the idea. And there are some tricks, like if you have two incoming gradients, maybe this intermediate computation h was used at two different places, then you can find the gradient of let's say g1 plus g2 with respect to a by just adding those two gradients. Okay, so you can just add gradients if you want. And similarly, if a is a vector and h is a vector, okay, so let's say a is p cross one dimension, b is q cross one dimension, and h itself is r cross one dimension. So these are all vectors now. So what is an example? Remember when we computed scores, that f of x comma parameters, let's say that's one huge computation node, was essentially a vector, right? So f was p dimensional, the output was p dimensional, x was d-dimensional, w was a parameter which was p cross d dimension, and b was p cross one dimension, right? So there was some, these are all vectors, and maybe one of them was actually a matrix. But when you have something like this, then you can still do the same idea. You just have to deal with matrices now. So these are called Jacobians. So if you take a multi-dimensional output, multi-dimensional function, then you essentially have what is called a Jacobian. So this is a Jacobian. So you so still do the local gradient times the incoming gradient. Okay, so it's just that the incoming gradient is a vector, the local gradient is a matrix. That's the only difference from the simple computation that we did earlier. Yeah. Okay, the next couple of slides are just now abstracting out and saying, okay, there's some multiplication of local thing with an incoming, with something which is incoming. So I'm just trying to abstract that out as a pattern. What is the operation happening? So you have a node, it's doing some computation, taking some inputs, doing some output. So just think of it as any function, right? So I don't know, some of you have used Python already. So in Python, you would write def function name with some inputs and return something as an output, right? So that, you just need to have for any node. So this would be a node, a function that would have two additional like operations, like you can think of that as a class now. A node is a class which has two operations, where in the forward operation, you would get inputs from the preceding nodes, or somewhere you get these inputs, and you remember those inputs, and you also compute the local gradient. Okay, because you can compute gradient of h with respect to a at a given value of a and b, and similarly gradient of h with respect to b at a given value of a and b. Okay, this is the forward operation. And what you need to return is just the value of h, because that's what you want. You got some input, you want to produce output, so you return h. Now, a second operation related to this node would be if you get a gradient from the succeeding node. Maybe some node says, oh, I'm the succeeding node. Here's a gradient of g with respect to h. Then what you need to do is multiply this with these local gradients and pass it back. So pass the multiplication back. So you just pass gradient of g with respect to gradient of a and gradient of g with respect to gradient of b back. Okay, so those two additional functions is what you need to have. Okay, so that's at the node level, and you can, once you have at every node, if you can do a forward pass and a backward pass. Essentially, when I say forward pass and backward pass, I'm just meaning at a node you can compute local gradients and do forward pass as the usual, compute the output and set it off. And backward pass just means at a node, or somebody gave me a gradient of them with respect to me, then I just multiply that with my local gradient, my output with respect to my input, and pass it, give that as an output. Okay, if I can do those two additional auxiliary things, then I can have a way to find, basically do chain rule, basically do backpropagation in any arbitrary computation graph. If every node in the computation graph can do a forward pass and a backward pass, then as long as I can keep the computation graph nice, which is like a directed acyclic graph, then I can compute a gradient with respect to any output with respect to any input. Okay, so so you kind of so there's a lot of bullet points here, but let's just focus on two. Uh, so you just recursively pass the inputs to the next nodes and keep computing the output. Okay, and recursively traverse the graph backwards and keep passing the local gradient times the incoming gradient all the way to wherever you want to go, whichever node is you want to find the gradient with respect to. Okay, so this is just a pattern that you can think about when if things get complex, but we're not going to do this in most of the coding. So this is just what is the underlying ideas behind many of the modules that you'll see, like let's say PyTorch or Keras or TensorFlow and MXNet, or whatever the packages. Okay, this I'll skip. It's not a big idea here. So now let's go over to some code. So what I'm going to do now is just refresh what we did in the earlier slides, which is we were working with a model which is Wx plus b. This is actually a linear model. So a logistic regression model is a linear model, and we're going to look at how it performs on some synthetic data, and we're actually going to do two things. One is we're going to define the model, of course, define the model data. Get the data. We're going to define the optimization scheme, which means we will do gradient descent. Maybe not batch gradient descent, we'll just do full gradient descent, as in we're not going to take a batch or anything. And we're going to define the loss. Okay, so these are the four things we discussed earlier. So we're going to look at all four. And I think instead of looking at these snapshots, let's look at directly the code base. So any questions at this point about backprop before I get into the linear regression example? Sorry, linear classification example. Okay, if anybody has a question, you can put it on chat, but I am going to switch sharing. Yeah. So can everybody see my screen? I'll have to look at the chat. Okay. So okay, so let's see. What I'm going to do is not just show the. So that's a question. So the question is, are we building any neural networks using feed-forward method? So can it be kind of neglected? So so we're going to look at logistic regression right now in terms of code right now. The whole course is about neural networks. So we'll be building many different types of neural networks. Now, the current logistic regression model, I think I briefly alluded to earlier, is actually a simplest neural network where there is really no hidden layer. Okay, so and in particular, it is an example of a feed-forward neural network. So we are going to be looking at feed-forward neural network early part of next lecture. But today is an example of a feed-forward neural network, but we really don't want to call it that because we know it's logistic regression, okay, from 575. So it's just that's how you don't have to get confused with the names. Now, can feed-forward neural networks be neglected? I don't think so, because they work very well. But we'll talk about bottlenecks in terms of why people don't just use feed-forward neural networks and why do they have to invent all these newer architectures. There is several reasons for that. For example, for images, you can actually get away with a smaller number of parameters, which is what a convolution neural network also gets you. In addition to some additional structure that you're exploiting for images, it'll reduce the number of parameters, and lower the number of parameters, the better it is for you, And that's why we looked at the idea of batching. I didn't really motivate batching today because today is just an introductory lecture, but batching is really kind of essential whenever you train a neural network. In fact, maybe I'll share a link to you guys where they show, depending on the GPU, on the quality of the GPU, if it's a high-end GPU, then you can have a larger batch size. And if you have a low-end GPU, you can only have a batch size of 1, for example. Which means that the GPU's compute and memory sizes are not enough. And because of that, you really have to work with small batch sizes. Okay, there's a computational, at least technical reason for that, in addition to some theoretical aspects. But so that's I guess my answer to your question. So let's come back to this. So okay, so I don't know if you have used Jupyter before. So what I'm going to do is so give you a very quick. We only have 15 minutes, so I'll not give. So there's actually a link to how to set up Jupyter on your own server. I mean, if you have access to a virtual machine or something, you can have a look at that video. But because it's only 15 minutes, I'm gonna. Yeah, so this is the link, but it's on lecture 2. It'll tell you how to download, for example, a version of Python, which I generally download. It's called, I guess, Miniconda, but you can also use other installers. And that video, where is that link? So the video link is here. It shows you how to set up, how to install Python and how to get Jupyter notebook set up. Okay. Once you set up Jupyter notebooks, what you'll see is something like this. Okay. It'll open, and if it opens in an appropriate directory, then you'll see a bunch of bunch of files. I mean, the files in the directory here, and in particular, this directory is has the files that are relevant to this lecture. Okay. And in fact, this directory is essentially from our course website. So where is this? So if you go to this GitHub repo, I think, yeah. So you see there's a link on the left hand side called GitHub repo. Go there, and if you look at, you can download this whole folder. Like you can download the zip or variations like that, and you can go to a folder called notebooks, and that's this directory. Okay, it has what I call Jupyter notebooks, and that is what I just downloaded the directory, and we are looking at once I started Jupyter, I guess, server, then we are seeing these notebooks. Okay. So somebody asked a question, can we say logical regression is a feed-forward neural network? It is a specific instance of a feed-forward neural network. It is not, I mean, feed-forward neural networks can have many other things than just logical regression. Okay. So, I mean, nobody's gonna, I mean, this is just a subjective point. I mean, it is a feed-forward neural network, but it's not that important that we should remember it. Okay, so let's look at the linear classifier example that was in the slides. So for those who are new to Python, I'm just going to give some very quick commentary on what's going on in each. So the screen highlighted thing is called a cell, and there are many cells, and in each cell there's a bunch of commands that are executed. Okay. So in this cell, mostly there's some imports going on, imports of a very important numerical package called NumPy, which allows us to work with vectors and matrices and 3D arrays and tensors and so on. And this is a plotting library. This is some random number generator where you're going to use that to generate our data. And another package called Pickle, module called Pickle, and that package is used to dump data to disk. It's useful to write any Python, typically many of the Python objects to disk. Okay, something like CSV file, but it's not exactly a CSV file. CSV or any of these Excel sheets or text files or something. So let's look at the more interesting cell. So sorry. So in this cell, what we're doing is reading data from a file called pickle. Okay, data x.pickle and data y.pickle. Now, where did I get those files? I just created a simple script which will generate the data. Okay, so it's actually just I want to get 100 observations per class. So what I'm trying to do is create a synthetic data set which has 2 dimensions and has 3 classes. Okay, and you saw the picture earlier of what the data set looks like, but basically this is how you generate a data set. All you're doing is so this particular code doesn't matter. You can always use a random number generators to also do it. But here we are using a specific deterministic way of generating those data points. Okay, and then once you generate those data points in a essentially a numpy arrays, which are these numpy arrays, then you're just dumping it to disk, which is the local directory. And here I'm just reading it from the local directory and plotting it. And so here you can see the plot. So this is the plot. This is the data set. Okay. Um, so the data set is essentially has 3 classes. I don't know if you guys can see the yellow class, but you can see the dark blue and the dark red classes. So there are 3 classes here, and they're circling around. So you can see that maybe a linear classifier with linear classifier by its name has to create linear decision boundaries, and so a linear classifier may not really work well with this 2-dimensional data. Okay, but it's just but let's move forward. Okay, so I'm just so now I'm setting up the so that was the data. That was the first component. The second component is the model. So the model is going to have two parts of the parameter. One parameter is w, which is going to have we have the number of classes is k, and the number of dimensions is 2, d is 2. So we're going to create a matrix which is d cross k. So it doesn't matter whether it's d cross k or k cross d at this point. We just have to multiply it correctly. So here it's all transposed. So you can see that b is 1 cross a k vector rather than k cross 1. So it's just transpose notation. Okay. So the w and b are defined here, and then we also defined the lambda value, which is 10 to the power minus 3 here. So in the next block, and this is where I'll actually interpreting this block is an important part of your assignment. So I will not give you all the details, but the most important thing is to show that this part is actually defining the loss as well as the optimization scheme. Okay, so the step size is the parameter inside the update scheme. Remember the W0 B0 to W1 B1, there was a alpha times the gradient. So W0 minus alpha times the gradient. So that alpha is 1 here, 1 e to the power minus 0 is 1. So what is this for loop? This for loop is the iterative loop where we're going from W0 B0 to W1 B1 to W2 B2 and so on. Okay. So what do you need to do in the for loop? In each iteration, you need to figure out, given the current W and B, okay, the current W and B. So currently W and B are set to some random numbers, okay, that you can see at the top. For the given W and B, for the given data set, we are actually doing a vectorized computation of scores, okay. So this is a vectorized computation. So remember, for each example, the input example is 2-dimension. I need to produce 3 scores because there are 3 classes. So that's what I'm producing, three scores. But if you look at the dimension of this course, a variable, it's going to be not just 3, it's going to be 3 times 100. Okay, 100 because we have 3 times 300 because we have 300 examples in our input data. Okay, so if you look at x.shape, it's 300 rows and 2 columns. Okay, so from scores, there's a way to convert to probabilities. I think we briefly discussed that because scores can be between anywhere, doesn't have to be between 0 and 1, whereas we want numbers between 0 and 1. So we can talk about the loss Li. Li was negative log of the probability. So that's what here, we're computing that here. So remember this whole code is vectorized. So we first compute the negative log of probabilities. That's the, actually it should be correct. But doesn't matter. So, and then we can compute the loss, which is the sum of these negative log probabilities for each I. Okay, and then you add the regularization as well in the next step, and there's some debug printing here. So from this line, so from here to here, we just computed what is the loss for the current choice. What we're gonna, sorry. Next, yeah. Next here, we're computing the gradients, okay? And although here it looks like the gradient computation is messy, not just that, sorry, from here to here, we're computing the gradient of the loss with respect to W and gradient of loss with respect to B, and that's captured in DW and DB, okay? So DW is gonna be the same size as W, and DB is gonna be the same size as B, okay? And because they're the same sizes, actually DW is also including this, because they're the same sizes, we are doing this gradient update. Okay, W is equal to W minus step size times the gradient of loss with respect to W. And similarly, B1 is equal to B0 minus step size times gradient of loss with respect to B. Okay, so you can actually run this, and once you run that, you get a final W and B. So for final W and B, I'm just going to use test data as the same as training data, which is not the right thing to do. But once you do that, once you do that, and you can plot your classifier. Okay, you can plot how your classifier is doing. In this toy example, you can see that this linear classifier is actually creating these linear decision boundaries, and that's kind of expected because it's a linear classifier. It's a 3-class classifier. In fact, it's just doing logistic regression, and this is something you guys can verify. Let's chat on Slack or as needed. So this is the classification. You can see that for the red region, many of the points are in red, but some of the points are also in other regions. Okay, and that's the limitation of a linear classifier. So you will see that even using a single hidden layer, and so that's where we'll get into a more, I guess, slightly more richer model, which is a simple feed-forward network with one hidden layer. That allows us to capture the trends in this data and really achieve very high accuracy and very low misclassification error. And so that we'll see in the next class. But try to have a look at this classifier example this week. Okay. So let me stop the sharing there. Okay, to conclude, any questions at this point? Okay, we are, how can I join the Slack? Drop me an email and we'll set you up. And let me summarize. So what did we do today? We looked at what was the objective of this course is to give you yet some more data modeling tools. And so that's the context. But the models themselves are a small part of a full data science solution. We looked at data variety and long-term versus short-term, as in model updating, which was the online learning part, and the deep learning part, which could deal with unstructured data. And we reviewed classification. There were 4 components, basically the model definition, which models are you going to work with? What's your objective? What is considered the best model, which is captured with a loss function? What is the optimization scheme? Typically it's going to be a gradient-based optimization scheme for most of our deep learning models, but you can use doesn't have to be the gradient descent based techniques. You can use some other optimization schemes, and we will mention it later as we go along. And finally, and the description of the data itself. So data models the optimization scheme were the key important parts, and the loss function. And finally, we discussed backpropagation. So it is essentially chain rule, but the objective of that section was just to say, oh, chain rule, we can always derive, if you look at derive gradient with respect to gradient of an output with respect to its input using hand calculation, using calculus. But to just get a sense of how a computer would do it, is that it would see, oh, if you want to compute from some input to some output, it will visualize that computation as some sort of a computation graph, and then maintain these local gradients and compute, multiply them with incoming gradients, and do this back propagation to compute gradients analytically. Okay, so that's how many of the software packages like PyTorch and Keras or TensorFlow do it. So that was the intuition we wanted to get from that. So those are the things that we covered today. Next class we'll look at feed-forward neural networks and start thinking about convolutional neural networks. That's all for today's class. And if you have any questions, as I said, start using Slack and reach out to the teaching staff for any issues. Okay, thank you, everyone. If there is any questions, you feel free to stay and ask. Otherwise, you can leave.
Yeah, so I heard, so for logistic, we didn't apply like a sigmoid function, right? But instead we did the normalization for the output. Is it like a same thing?
It's the same thing, yes. So that's a very important part, and that's going to be important for maybe for assignment as well. So the logic regression that you saw today seemed like a linear model. Okay, so there was no sigmoid thing going on explicitly, but the scores are getting transformed to probabilities, and that's the sigmoid uh, aspect. That captures the sigmoid aspect. Yeah.
Okay, okay, cool. Thank you.
Any other questions? Yeah, most everybody can. We're out of time, so definitely head out if you have other things. And if some people want to stay and ask questions, then please go ahead and ask.